Is this a civil engineering?
Nope.
Nope. Okay.
Computer engineering. You guys are M16, right? No? Okay, it's fine.
5420 is where
Yeah. That's the room for my discussion section.
Huh.
Let's see. Or am I in the wrong room? Just a sec. Okay, maybe I'm in the wrong room. No. It could be that I'm in the wrong room. So just bear with me. Yeah, I think I'm mixed up. Sorry. I'm mixed up. Okay. None of you spoke up. That's what this works. Okay, great. Hello. Can you lower this volume? Testing. I'm still coming up. Maybe just disconnect from audio.
Try something.
Testing. Great. And why is it not showing the screen? I am sharing. I think so. Let's see. Okay, great. Awesome. Thank you.
Yep.
Okay, good to see everyone in person. So just firstly, sorry about all the confusion that's happening. So you probably saw my Piazza postings that the Thursday section, unfortunately, we can't do it on Zoom because without university's approval. And so anyway, long story short, that's going to be in person. I know some of you wanted to shift discussion section. So 1D is now in Royce Hall, which is a big room. So we have kind of some headroom there. Looking at the registration, it seems like 1C and 1D are the more in-demand sections. So hopefully it gives a little bit of a headroom there. Okay. So want to just, again, I had rushed through this thing last time. So just going to spend a few more minutes on the logistics part. So the course will consist of assignments of two types, problem sets and design assignments. Design assignments, we are going to use a tool called LogiSim, which lets you design digital systems and simulate them. So kind of there will be some assignments which are around that and some assignments which are on great scope problem sets. We'll have quizzes. You can think of them as similar as similar as assignments, but they are going to take place in a particular time slot and time enforced. Okay, so that's really the only difference. The structure would again be submission through great scope. What we are thinking this time around, remember I referred last time, yesterday, that we are going to do some personalized questions. So what we are setting up is a system where you will download a notebook, a Jupyter notebook. Hopefully some of you have at least seen it, or if you have used Colab on Google, it's kind of similar in style, but essentially it would be personalized to you. You're going to fill that out and you're going to upload that on Gradescope. So that way we can have questions which are some questions or some aspects of the questions are personalized. Same thing with the quizzes, and yet we can auto grade them. So that's the plan. Final examination is going to be in the final exam slot. So unlike previous offerings of the course where final was a take-home design assignment, this one is in class, in room, in the final exam slot. Again, an online assignment. You can come to the room, the TAs will be there in case you want to ask questions or something, or you can just do it entirely remotely and we'll be on Piazza. And some grade set aside for discussion section attendance and problems that the TAs are going to hand out. So doing those. In terms of when the quizzes would be, kind of anticipating around 4th week, around 7th, 8th week, and the last lecture. Okay, so that's what kind of the plan is. Let's see. So on to the grading schema. The assignment. So for any given piece of work, quiz, final exam, assignment, I basically normalize so that the median of the class is 80 if it was lower than 80. If it is higher than 80, then it remains unchanged. And the way we do the thing is the median shifts to 80, the highest score, generally speaking, will shift to 100. But if you look at the formula, there's an exceptional case. I'll let you figure that out. And if you get a 0 score or don't take the exam, then your raw score is your normalized score. So no credit in that case. And then eventually we add everything up and sort of assign grades. These are at least, so if you get 90 or higher, you're assured some sort of an A, but there may be some A's below 90 and so on and so forth. I guess a few comments out here because every year we kind of struggle with this. So just remember, because I normalize, absolute score is not something you should worry that much about, because sometimes we may end up giving a problem which turns out to be harder than we anticipated. We didn't do our job well, but this median business takes care of it. The scoring, I'm not going to second guess what the TA or the reader did unless there was something wrong in our solution or our question. Given the class size and given the fact that after the grad student strike, the ratio of undergrad students to grad students in the classes have blossomed. And so we have all the more reliance on technology at this point. And unfortunately, one of the things is these auto-grading kind of technologies, which have the disadvantage that they can't parse nuances. We can do wrong or right very easily, but we can't really quantify how much wrong you were. And also the substitute is we do a lot of questions and kind of statistically rely, or a lot of tests in case of design assignment, and kind of rely on that, on balance that will reflect the reality. So unfortunately, we can't really do much of that traditional partial grading that I got this right, I got that right. It would be a bank of tests that we are going to work with. Having said that, the exceptions will always offer you the ability to request a regrade, and we're going to look at it. Sometimes the issue is that our question language was not very clear, and also in that case, we'll certainly consider it. So that's just that point. And late submissions. So again, particularly for a class size like this, making all sort of approval exceptions for late submission, and also I don't do that. Instead, my policy is simple, works like this. You'll have a budget of 8 calendar days for the quarter to use as late days. It's your responsibility to track them along the way. So it's not like there's a website you can go and say how many I have used. We will just at the end sort of work through that. You can use them towards problem sets and design assignments, but obviously not for quizzes and the exams. You must use them before the Monday of the finals week. So you can't, if something is due on Friday of the finals week, you can't just say, okay, I'm going to extend it into the finals week. So that we won't let you do. No more than 3 late days can be used towards any single assignment. Some of these things are simply because I need to be able to grade and hand out the solutions. So we really can't just have ad infinitum sort of request. Late days are used in chunks of 24 hours. So if you exceed by even 1 second beyond the deadline, you have used up a late day. So just bear that in mind. Do keep in mind that since your submission is through Gradescope, just make sure that you have good internet access and stuff like that. I build in a minute or 2 of Slack typically, just to avoid these things. But even then, I mean, I hear all kind of interesting excuses and all at times. I really can't do much about it. You'll use the late days. What surprises me is that despite, I think, I mean, I know how many late days are given in some of the other courses. I think 8 is pretty generous. And what often happens is early in the quarter, you are doing frat rushes, things like that. You use up your 8 days and now you are left with nothing. Whereas in reality, you need them more towards the latter part of the quarter when you're squished for time with your other obligations. And also, I really urge you not to use your late days early on when the assignments are simpler, because if you end up using them, you will have a really hard time towards the latter part of the quarter. So leave them for the for later use. Okay. In fact, if you pace yourself right, you can actually make your life easier for other courses by making use of late days here. Don't use them early on. So we will not give you extra ones. Okay. There is, for everything that I said, the only exception is if there is a university approved medical reason that requires me. Now, having said that, those medical reasons do not apply to assignments. So late days really don't matter. They only apply to timed quizzes and timed exams. So we'll just follow what the student counseling office requires me to do. Okay. So in terms of but as we are moving towards more of this online assessment, online submission, of course, the issue of cheating and sort of exchanging notes and all always comes up. Every year, in recent 4 or 5 years, I have had roughly 10% of the class go through honors code violation. So I'm pretty good at detecting these because the same on detection tools, the same tools we use for grading, also actually kind of assist in that process. So it is truly an honor system, but don't test it because we generally figure it out. I'm sure I've missed some. You can use any resources. Okay, want to ask ChatGPT, be my guest. Yeah, the only thing you are not allowed to do is to ask any human being, including yourself, even if it is through an electronic medium. So sort of talking to someone or by email or Discord and all counts. But you're welcome to use any tool, consult any paper, any other textbook. You find solutions to something in the web, that's fine. I can't police them, so I'm not going to ban them. So this way the playing field is even. All of you are free to do it. Design assignments and problem sets. Some of these things will have pretty strict requirements on how you should format your submission, how will you name the inputs and outputs of your design, and or what you are allowed to do or not allowed to do in terms of moving things around in a circuit, in a digital schematic. And the reason is that's the only way we can grade. If you kind of change names and all, the autograder is going to fail. It's kind of like in a program. If you give different names, then we can't grade them. So make sure to sort of read the instructions. A lot of time I have seen that the students lose points because they don't read the instruction. And I'm already seeing that, like the Piazza post Obviously, the students didn't read that the class was going to start at 5 p.m. So just read the mails. I think it's important. What happened? Okay, sorry. Okay, so quizzes are timer enforced on Gradescope. I don't know, have any of you done those timed quizzes on Gradescope yet? No one ever. So the way it works is from the moment you access the quiz or exam, timer will start counting and you have until then to submit. Gradescope officially says that you should explicitly submit. In practice, I have seen that it does do some sort of an autosave, but I don't know how frequently it does. So make sure you periodically do an explicit save as you kind of go along. Quizzes will be during lecture hours, and exam would be during the final exam slot. Again, the only exception would be if you are approved for some additional time, then that time may go after the lecture or after the final exam slot. Okay, so you just continue and then you have extra time. You'll have to make sure that you set that time aside on your schedule. So we will not let you stop, go home, take, resume. We just can't do that. You just have a block of time. So, okay. Cheating, plagiarism, like I said, don't do it. You'll get caught and then the penalties are much more severe. Last year, there was an interesting case where I caught the 2 students denied, and then eventually they admitted. And that made matters worse because it basically boiled down to that statistically what they did was just 1 in like gazillion zeros after it. Okay, the type of problems I offer are one which we're highly unlikely that 2 students in the class are going to end up with the same thing. Not all problems are like that, but a lot of what I do are kind of that nature. So don't push the boundary. It's just not worth it. We're going to use this tool called Logisim, specifically Logisim Evolution. It's basically a graphical tool. Some of you have accessed Circuitverse, kind of similar in style. All these tools, what they let you do is they give you a library of digital modules, like adders, multipliers, stuff like that. And then you can wire them up to create more complicated things, much like if I were to give you a library of software functions, then you create a more complicated program out of it. So if you go on Piazza, there is a link for Logisim Evolution. The latest version is 3.8.0. Download it, install it. It's a Java program. So you can run it on Windows, Linux, Mac, all 3. One just thing I just want to point out is 2-3 weeks ago, Apple had an update to Sonoma 14.4, which actually introduced a bug that would crash all Java programs. So make sure that you have installed 14.4.1, which is the latest release, because we went through that phase where Java programs won't work. There are a bunch of Logisim is used at many universities all over the planet. So there are a lot of videos and all on YouTube, for you to consult. I've sort of given one, and again, some of them are accessible through the Piazza resource. Yeah. So so my slides are labeled modules because usually a module may span multiple classes. So that's kind of the intent there. So we are going to start with low-level representation of information digitally. How do we kind of deal with it? And in fact, the mathematical underpinnings of that are what is called as Boolean algebra. Some of you may have seen it in some math courses, logic. If you've done a course in philosophy or logic, you may have seen it. Then we will move to designing what I would basically say complicated digital systems from either from some sort of a specification like equations or some other mathematical representation, or from simpler pieces. So kind of 2 ways of doing things. I specify and then I synthesize from it a digital system, or alternatively, I give you simpler digital systems and I ask you to wire them together to make a more complicated digital system. there are two types of systems that we deal with. So if you would see out here, combinational logic. And combinational logic refers to things which are just like pure function. I give you some x and you produce some y. Okay, y depends only on x. There, in particular, it has no memory. Okay, it doesn't depend on the history. So these are just pure mathematical functions. And then later on, we are going to look at systems which are called sequential logic. These are systems with memory. So they can answer things like, have the number of cars that have crossed my went past my house, is it even or odd? So these are kind of questions that require you to not simply look at what's happening right now, but really have some sense of what happened in the past. So these require memory, and this is no memory. Another way of thinking about that is in a programming language like C++. Hopefully all of you have seen it. If you write a function which takes an input, produces an output, and internally doesn't remember anything, so that next time you call the function, you have no memory of what happened in the previous invocation, that's like combinational logic. And then if you use so-called static variables, or if you store something on disk, or somehow like you remember what happened in the previous time you ran the function and then reuse that this current time, that means you have some sort of a memory, and that would be sequential system. And then we are going to look at things like, how do you represent numbers? Because while digital systems correspond to any set of discrete values, our most common use for them is, or at least a very common use for them is to do arithmetic. So we have to be able to represent numbers. And so there's a lot of effort on like, how do we represent numbers of different types in the form of, in a digital logic system. And then we're also going to spend time on how to make our life easier by taking something super complicated and breaking it down into a particular style of creating a digital system. So in particular, there are these concepts like data path and controllers. Basically, we think of these systems as having two parts, part which processes the data and the part which makes the decision. And all computers, all digital systems tend to kind of have this structure. So we're going to talk about that. Then we are going to spend some time on topics like, how do you design system for meeting certain timing requirements? So it's not simply enough in digital systems to produce the right value, but you also have to produce the right value at the right time. And or sometimes it's simply saying, I want it quickly. Other times, some precise order, like I want this output to appear 50 nanosecond after some other output. There might be some very tight requirements. So how do we design systems which have that? How do we design systems that can be made fast? And also, how do we use some of the tools and all out there? So those are kind of things. Not everything here, unfortunately, we will cover, but some of it. And I guess one final bit, I mean, this is really the opening course in a whole bunch of digital systems related coursework that exists at UCLA. Those of you who are computer engineers, you're probably going to do digital design lab. You're going to do courses where you get into embedded systems, like more complicated things where software and hardware come together. You're going to look at architecture of computers. If you're in CS, you do a major digital design project. If you're in EE, you also dive deeper into how do we make these gates and all. So there's a whole slew of courses, and of course, there's a whole slew of courses at the grad level as well. So what you should perhaps do sort of this week, just make sure, download and install LogicSim, read the documentation, familiarize yourself. Okay, I think in any profession, you will be only as good as how adept you are at using the tools. And so spending that time upfront kind of really helps a lot. Do make sure to, if you haven't already, a lot of the postings that went on Piazza. Anyone here who is unable to access Piazza? Okay, everyone. I post the slides a few days in advance, so you will have access to it. If I correct them because of some mistake that got pointed out during the lecture, then I'll re-upload, but hopefully there aren't that many. I used to use a different software setup so that the slides would be annotated as I would annotate them, but now I'm using the Zoom annotation. Unfortunately, it only appears in the video. And I kind of thought about it, and I felt that actually that's a good thing, because what I was realizing was that a lot of students were never not coming to the class and never even watching the video. So they were just looking at the slides and my annotation, and that's it. So I think, in a way, it's a good thing, because if you want to see the annotation, you have to watch the video. And I want you to watch the lectures, because otherwise, why are you paying the hefty UCLA tuition if you are just going to have the slides? The slides are on the website. So kind of, hopefully, if the course is super trivial for you, then of course you can still do it without listening. So annotations are only in the video. I guess that's a long-winded way of saying what I. So yeah. So before I move to the main lecture, module number 2, questions, or anyone on Zoom, if you have questions, speak up, please. Okay, sounds like not. So now we are going to. So we are going to spend this pretty much all the time today on how do we represent information digitally. What do we mean by that in the process? Okay, so this, if you have the textbook, then that's chapter 1. So essentially, like I mentioned in the first module, digital systems are those where we deal with discretized inputs and outputs, right? The inputs are some discrete set, outputs are some discrete set. Internally, the system deals with information in that manner. A special case of that is when the input is binary. Binary means 2, so kind of a special cases if the input can take 2 values, 0 and 1, for example, but it could also be apples and oranges or red and blue, right? Just 2. So, of course, a system can have multiple inputs. So I may have multiple binary inputs, for example, right? In that case, that's like if I have k inputs, each one of them is binary, then I can represent how many inputs, distinct inputs. So if I have k inputs, each one of them is binary, then how many distinct inputs can I represent? To the power k, right? Okay, so I can get to the power k one of 2 ways, right? One is have binary inputs and k of them, and the other is a single input with 2 to the power k possible value, right? They're functionally equivalent. Implementation wise, they might look sort of different. So now comes the question. So like let's take an all of you have hopefully seen C++. What is used in CS31? C++? Yeah, okay. So in C++, we have these data types like double, right? To represent numbers which are real numbers, right? How many distinct values can a double in C++ represent? Right, it has 64 bits, so it can only represent to the power 64. Excellent. And so out of the infinitely many possible real numbers, it has to make a choice on which to the power 64 it represents. And actually, it represents a bit fewer. Some of the combinations are not valid. So that process, deciding how to take what I have to represent, namely real numbers, into the finite number of bits that any real computer has, that's the process of encoding. I have to decide how to encode. In case of double and other such numbers, there's a standard IEEE 754, which kind of dictates how to represent that. But so we'll see how kind of we bring that. Okay, so let's talk about it. So system, as we said before, anything which has an input and output, and it processes, stores, communicates the data. So system can do a whole bunch of things, right? It may simply transform the value. It may store, remember it for future. It may send it to whatever, some other entity on the planet, and so on and so forth. And these signals could be realized physically by variety of means. They could be electrical, they could be chemical, mechanical, pneumatic, optical, quantum, any type of thing. So the whole idea of digital systems and logic and all is independent of how we implement it. Having said that, the reality is that almost 100% of digital systems in existence today are done using the semiconductor technology that I described last time. So they are electronic, but they were not always like that. As we saw, transistor was invented in 1940s. Prior to that, we had electrical computer, but they used relays, electromagnetic relays. That's how the computers in early 40s were, or even mid 40s. And prior to that, prior to even like you go far back before those things existed, they were mechanical computers. Okay, in fact, if you go to some of the old museums in Europe, there's a long history of mechanical machines which compute stuff. Vacuum tubes also. So relays and vacuum tubes both existed. Thanks. Yeah. So both were used. Relays were used quite a bit in telephone system, and vacuum tubes were the one. Yeah. Relays were more reliable, vacuum tubes less so. So yeah, both they kind of existed around the same time together. But yeah, excellent point. And there have been other computers, like for example, right across the courtyard. Okay, wrong side, left side. Yeah, so in the chemistry building, actually the molecular computing work got a lot of fame out here. That is, they were making computers where the state of the molecules represented information, and they were creating molecular transformations as a computing mechanism. Nowadays, the hot thing is quantum systems, okay, quantum computing, and again, kind of a lot of cool work happening in that space too. Okay, so let's look at something like a car. Car is a system. It takes inputs like when we press the accelerator pedal or press the brake or move the steering wheel and so on and so forth. And of course, the output is it drives, it provides torque onto the wheel so that the wheels move and the car moves. So if you so depending upon kind of how you define a system can then be part of a bigger system. So like a car could be viewed as a component of a transportation system in a city, for example, right? So we can look at it at different abstractions. Almost anything that we kind of think, you can think of it as some sort of system, and systems abound. Digital system take input and output in a discrete valued manner. So any type of thing, value could be open, close, 0 through 9, A through Z, set of colors, so on and so forth. There's no like any, the only requirement is a set of discrete values, but it doesn't need to be electrical. Again, most common realization is that we think of each individual input to be binary valued with a low voltage and a high voltage. So 2 values, okay? That's the most common thing, but there are systems where any given wire or signal can have more than 2 values, okay? That is still discrete, that's still digital. It's okay. One of the most, I guess, famous examples of some of the early computers of this nature was the machine that was used to break the German cipher by Turing. So this is one which actually uses electromagnetic relays and all, not vacuum tubes. So if you are ever in kind of Bletchley Park area near, I think, on way to Oxford from London. It's a beautiful museum, and they kind of go through the whole history that how kind of they broke apart, or watch the movie Imitation Game. So it kind of goes into that. But there's a longer history prior to that. There was Charles Babbage's difference engine, which was sort of mechanical, basically. And again, they a few years ago, I think late in 1990s or something like that, I think. Yeah, they kind of rebuilt it based upon the designs that were available. So these kind of things have existed, and there's actually they're pretty interesting in a way, in the sense that the complex things they are able to do from something which is just gears and stuff like that. So at some level, it's pretty marvelous. Of course, that's not how we build the computers now. First programmer. I don't know how many of you have heard the name Ada Lovelace. Ada is also the name of a programming language in her honor. She was the first programmer, although nowadays we associate computer science with dominantly male, but it actually started out with a female programmer being the first programmer, and she was the one who was responsible for programming the Babbage's difference machine. Okay, so now becomes this issue. Remember last time I talked about world is analog. A lot of things we deal with are continuous value, and yet we process them digitally. So a question that appears there, at least hopefully you would ponder about it, that in the process of discretizing, do we lose information, right? I mean, if I have a waveform of sound corresponding to, say, music, if I'm going to discretize it, then I have to make some choice. How many discrete levels? Do I lose information in that way? How often do we sample it in time? Do I lose information in that, right? I mean, so discretization in time, discretization in value. So if I look at continuous signal like this, if I look at the continuous signal like this, and then if I sample it in time, and then if I sample it in space, in value, I will end up with something like the following: that at every time instant, I measure conceptually, I measure the value, continuous value, and then I put that continuous value in one of the discrete bits, right? So let's say at any point in time, I would quantize it to 2 values. Then I will have a threshold above which it would be 1, below which it would be 0, for example. So the question then, so then what happens is, if I discretize this way, question then becomes that the new information I have, which is a sequence of numbers, basically, is that enough to represent information that I had in the original waveform, or did I lose something? And intuitively, the finer granularity with which I sample, closer am I to the continuous reality. And so both I should sample very frequently, and I should sample with lots of bits, okay? Now, if I take a continuous signal, right, let's say measuring sound level, okay? Well, the reality is that when we hear sound, we have a limited ability to distinguish between different sound levels. Let's say there was some sound source and you were listening, our ear and our brain's ability to distinguish between sound levels which are very close is limited, right? I mean, we will not be able to distinguish between them. So even in the value dimension, discretizing too finely is pointless, because we cannot distinguish between bits. And that is because there's enough noise in the system that it really doesn't make sense to us. So when we are discretizing values, there's a point of diminishing return, that beyond which having finer scales doesn't matter. And that is really a function of what the type of signal is, right? So usually when you have something like music, you would see things like, they would say it's 12-bit or 14-bit music. What they're really referring to is that the value of the sound waveform is being quantized into 14 bits, 2 to the power 14, which means 1 bit represents a value which is 1 over 2 to the power 14th of the overall signal. And that's so tiny that we can't distinguish it, right? So the name of the game there is only pick as many discrete levels, as many bits as are necessary to do the job, because any finer than that, no one can tell them apart anyway. So that's about the value. The question of time still remains. How fine should I sample in time? If I'm sampling it every 1 second, every 0.1 second, every 1 femtosecond, what gives under what circumstances. Now, intuitively, you would say if the signal is very rapidly changing, I should sample more frequently. And if the signal is kind of a slow type, then I should be able to get away with slower frequency sampling. And that kind of, in a way, is a statement about what frequency the signal is in. So if I give you a waveform, we can define something about like what frequencies it has. If I have a sine wave, I know its frequency. But if I have a more complicated signal, how do we figure out its frequencies? Go to your math courses. How do we do that? How, given a signal, given a function, can I talk about what the frequencies are? Imagine a signal which is addition of two sine waves. It has two frequencies in it, right? F1, F2. If I have a signal with 100 sine waves, addition of 100 sine waves, then it has all those 100 frequencies. So in mathematics, there is this whole notion of Fourier decomposition. Anyone heard of it? Fourier transform? Yeah, some of you know, right? Fourier transform, the coefficients of the Fourier transform are the frequencies in your signal. Okay, so I can go between a time waveform into the Fourier transform. I can get into frequencies. The reason it matters is that there was a very profound result roughly a century ago, 1920s. It's called Nyquist sampling, and later on refined into something called Shannon-Nyquist sampling. And basically, it made this very bold claim that while intuitively it may seem that sampling in time should cause loss of information, because I don't know what value existed in between, but that is not really the case under some reasonable setting. So if I give you a waveform like this, if I were to sample it, you would say, hey, I don't know what the value is here. So can I ever recover it? So what these guys said was that there is, under some circumstances, I can sample at some finite points and still recover it. So what are those circumstances? They basically, so firstly, I hope kind of I convinced you. If I don't tell you anything else about the signal, then there may be, all you have are these red dots, which represent where I sampled. Then there are many ways, there may be many signals which can go through those dots, right? I can have this, or I can have a different signal. They are all valid ways of connecting those dots. But what this Nyquist sampling says is the following. It says that if I have a signal whose maximum frequency I know, and if I then sample it at twice that frequency, so let's say I have a signal which has sine wave components only, and the highest sine wave component is 1000 hertz, then Nyquist sampling says that if you sample it at 2000 hertz, so 2000 samples per second, then using a particular way of recovering called sinc interpolation, I can recover the signal perfectly. So long story short, if the signal is limited by the maximum, if I know the maximum frequency of the signal, then I can sample at twice that rate and still recover the signal. You'll learn more about it in those of you who are in ECE, you'll learn more about it in signal processing courses. Interestingly, some research around 15, 20 years ago, a lot of it here at UCLA and Caltech, showed that natural occurring signals, right, have a further structure to them. And actually one can sample at even lower rate and still recover them perfectly. Okay, so a lot of advances have happened. So long story short, I can sample a signal, convert them into discrete time and discrete values, and effectively not lose any information. Right? Okay, that's the long story. So that's why digital computers or digital systems make sense. If we had if there was no way to go from the analog world to digital world without losing information, we would stick to the analog world. But this is what gives us a way out. Any questions? I'll just take a pause out here. How many of you have seen this sampling business? Some of you, I guess, one or two, or which course? Yeah. Okay. Okay. Anyway, so So let's now take this. Yeah, please. Sure. Sure. Okay, so let's now look at the binary. So a special case, the simplest case of discrete value is binary, two values. Why do we use binary values a lot? Because what do you think? Like, I mean, so most digital systems at the lowest level are a collection of binary values. Why do you think that's the case? Why don't we use other values? After all, we have 10 fingers. 10 might be a reasonable number, right? I mean, there are a lot of other options. Why do you think choice of 2 is good?
It's easy to represent.
Why? Why is that? I mean, I can represent multiple values also in hardware. It is easier, but not easier is okay. I'll take that, but yeah, okay. But I can certainly represent other values in hardware also.
Because electrical circuits are on or off.
Yeah, so on and off is the easiest. Remember, I talked about transistors, on off, right? So our basic working horse is like that. Another thing is, if you have just 2 levels, then it's the most robust thing you can do, right? Let's say, how will I represent values in electrical system? Let's say, right? I will represent them by voltage or current. Those are the 2 values I have. How might I represent them in a chemical system? Let's say concentration of some molecule, right? That's how things happen in a brain when neurons fire, right? Concentration of chemicals building up, and that results in neurons firing. Thing is, the world is full of disturbances, and dividing any value into the 2 extremes is the most robust thing you can imagine, right? It will take a lot of perturbation to switch 0 to 1 or 1 to 0, right? I mean, whereas if you do a finer partitioning, then you are kind of more fragile, more prone to disturbances. So that's another reason. So ease of implementation and this. So it's easy to manipulate zeros and ones, and they are more robust also as a consequence. So the challenge is really then boils down to how do I physically represent these discrete values, right? It's one thing to build a conceptual framework where, yeah, we have zeros and ones and all, but then how do I actually represent? So it would help if the physical quantity we are dealing with is also discretized, is also discrete. So now, of course, like I referred to the fingers of our hand, that's discrete. That's clearly discrete. So if I were to be designing computers by using fingers for computing, then discrete values, we have discrete number of fingers. Gears is another example. It's naturally discrete, right? When we make the gear, it has finite number of discrete number of teeth, and so it's naturally discrete. So I can map my discrete set to positions of the gear. That's great. Actually, one of the first mechanical computer in this country was right here on UCLA. If you go to our school's website, you will kind of read about it. I think there were 4 of them which were put in 4 different universities in the West Coast. This was the only place. It's kind of ironic that all computing industries in Silicon Valley, because the first computer in California, first electronic computer in California, they were all around Westwood. Original history out here. And for a long while, this mechanical computer was here at UCLA, and then I guess in 1970s, I believe, is that they donated it to Smithsonian. So that's where it is now. So you can read about it. There is actually also a pretty nice movie describing it. Also, I'm not going to play it. A little bit cheesy also, but it kind of gives an image of UCLA being this super nerdy place, which is pretty different from what you see on campus nowadays. But in any case, kind of a bit of a history. So they were using it for computations associated with physics for the most part. So yeah, so a bit of UCLA history there. So now the question is, so these were mechanical systems. They were using gears, and so gears have discrete positions and therefore naturally digital, right? But what if the system has continuous components? What do we do then? And so a lot of times we are going to design computers where the underlying physical variable we are using to represent values is continuous. Voltage, current, in our brain, levels of molecules, and so on and so forth. So let's pick voltage. In fact, in electronic systems, the most common representation is using voltage. There are systems which use current, but voltage is the more common one. So let's say I have a system which can work between two extremes of voltage. So I've just picked -0.3 and 2.8 out here. Below -0.3, bad things will happen. Above 2.8, bad things will happen. So that's our limit. Let's say, I mean, this corresponds to a real technology, but kind of idea is the voltage is too high, the system will burn. If the voltage is too low in the other direction, negative direction, again, the system will go bad. So I have some range to play with. How do I represent 0 and 1? So what would you do? Okay, so I can split it in half. That would be one choice. You can say all of this is, let's say, 0. All of this is 1. Anyone thinks this is a certainly it will seems reasonable. Do you see any problem? So let's say half was, let's say for sake of example, it was 1.5. And let's say I had voltage 1.499999, something like that, very close to 1.5. So we'll say it's a 0. But there's all sort of noise in the environment. It perturbs the signals, right? Even little things like the AC current flowing in this room, okay, stuff like that. Okay, so it just causes a little bit of perturbation and goes to the other side. Suddenly my 0 becomes 1. So if I simply divide like this, I'm creating a system which is potentially very fragile and can be affected by this noise. So what would you do then to deal with this problem? Buffer voltage, right? So I can do something like this. I can say I'll have this, I'll call this 0, I'll call this 1, and this is kind of like a no man's land. Okay, system should not be there. Okay, so we can play this game, and so let's see how in a real system this works out. Okay, so how to define the binary signal. So the way it works is the following: we are going to define two levels, in this case 0.7 and 1.7, and that's the level which the system recognizes as a valid low input or 0 input, or a high input or a 1 input. So we are basically saying to the just a sec. Okay. Okay. So so we'll basically define this thing where VIL is a value below which, if I get a value coming to the system, I will say it's a 0, guaranteed. Okay, and if I get a value coming in which is higher than 1.7, we'll say it's a 1. And it's my contract with whosoever is giving me the input that they should never give me a value which is between 0.7 and 1.7. Okay, so electronic design or these systems are dependent upon this under the hood contract that whosoever is giving me the value, it has to obey this. Now, remember, I talked about noise, right? As signals travel over wire or whatnot, they will be perturbed by all sort of noise in the environment. So when I output something, when the system I'm designing, when it outputs something, I have to give some additional margin. And okay, so we'll see how that is done shortly. So on the input side, this is where the picture is, that don't give me a voltage higher than 2.8, don't give me the lower than -0.3, and don't give me between 0.7 and 1.7. Okay, so that gives me what the supplier must obey or must obey. So, and what about the middle? This is for the very reason that we want the system to be robust. Okay, so small variations in the input will be kind of robust to them. This you can this yellow band is, you can think of it as a margin or a buffer, as you called it. Oftentimes called it a noise margin. I can tolerate that much noise. Okay. Now I must emphasize the voltage values I'm using out here are purely for example. They depend on the specific system or technology. Okay, so here is an example. If you look at data sheet, which gives the specification of, in this case, some particular chip called SN5400, SN7400. It's from Texas Instruments. And you would see that they give you these values of VIH, VIL, okay? So on the input side, what the voltage could be. So VIH here says 2 volt. And for this chip, okay? And VIL is 0.8. So it's basically saying on the input side, for the input to be considered high, and usually we call high to be 1, logic 1, then for it to be considered high, it should be at least 2 volt. And for the input to be considered low, it should be no more than 0.8. Okay, that's the interpretation out here. Okay, so that's on the input side. Now we have defined this value. So now let's look at what can we do on the output side. So before we do that, again, let's go back to the system. Kind of the idea is, as signals are propagating through wires and whatnot, noise gets added to them. So their voltage changes. Voltage can increase, voltage can reduce. So someone gave me an input, and by the time it actually came to my digital system F, some noise got added to it. So that someone who was sending me the signal, it thought it was sending me a 0, but maybe the noise which came to me made it a 1. It flipped the bits. So I have to so I have to kind of make sure that we are kind of robust to this, and that's why that margin. Analog signals have no mechanism to deal with this, which is why if you have like the old style analog radio, FM radio, AM radio, you kind of hear all sort of clips and sort of sound. Any type of noise in the signal is going to manifest itself. If you have an old analog TV, I don't know whether they even exist now, you would see snow in the picture and all, for example. Digital system have a nice property that they can tolerate this noise. So even if the signal gets perturbed, a 0, as long as the noise is not too large, a 0 remains a 0, a 1 remains a 1. And that gives us tremendous resilience. So even if noise gets added to the input, as long as it is below that margin, my system will still operate correctly. Okay, and it will produce the correct value at the output. So that's a big advantage, that small noises disappear, they're suppressed. Every time you go through a digital logic, it essentially is acting like a filter for noise, right? Getting rid of it. Whereas in an analog system, the noise kind of propagates through. If you have music system, imagine you may have seen kind of these ground loops and all these kind of things which can cause havoc with speaker wires and things like that. That's an example of the top here, which is noise flows through the system and you can perceive it. Whereas the digital one, it gets suppressed at every stage. Okay, so now the question becomes, if I'm outputting something, what should I do? So if I want to output a 1, in my example, what should I output? So usually in these systems, they define 2 other levels. They call them VOL and VOH. There's a little typo out here. Okay, VOL and VOH. And what these are doing is, we are basically saying that when I'm outputting something, then I am going to if I want to output a 0, I'm going to output a signal no larger than VOL. And if I am outputting a 1, I will output a signal which is at least as high as VOH. And this noise margin gives me resilience, right? Because what is happening is, let's say let's say this value is 2 volt, okay? Then I have a 0.3 margin. So it's basically saying someone can take my 1, which is 2 volt, add 0.3 noise to it, and the receiver will still see a 1. So we create these additional bands around it. And so what is happening is as a signal flows through digital signal flows through a complex system, one digital stage, every time we go through it, it kind of, the noise gets removed, basically. So that's the robustness part of digital systems, that they are very, very tolerant to noise. Of course, there are limits to it, right? I mean, there may be noise which exceeds the noise limit. There are sources of noise which are very powerful and they can flip bits and all. We can't go around it, but you try to make sure that the system is at least tolerant of commonly encountered noises. So you guys are all too young, but like I lived through the era where we changed from analog music systems to digital music systems. So compact discs came and then MP3 players and stuff like that. Before that, signals used to be encoded in an analog waveform on these records, which I guess are back into fashion. A lot of people are purchasing those discs, but you would hear all sort of clips and chips and noise and all. Some people loved it because it kind of gave a warmth to the music, supposedly, where the digital music was more crisp and all because it doesn't have any noise. Okay, if the noise happens in digital systems, you can even correct for it. So like you take a CD, no one uses CDs now also, but let's say if you have, you even scratch it and it can tolerate that, okay? Because once you are in the digital world, then we can play games with it to even take care of certain amount of bit flips in it, for example. So digital signals are great from that regard. So now if I look at a digital system and I look at its input voltage versus output voltage, it will kind of look like the following. On the input side, VIL and VIH are the two magic thresholds. And on the output side, VOH and VOL are the magic threshold. So on the input side, anything up to VIL is 0. And on the output side, if I want to output a 0, I will make sure that my signal is no higher than VOL. And VOL, as you can see, is smaller than VIL, right? So that's the source of robustness. Okay, I'm going to take a pause here again. Questions? So, takeaway.
Quick question.
Yeah, please go ahead.
So going back to the slide where you had like binary input, so what exactly is like
Which slide?
This side in the question mark region, like what do you like do there?
You should never be in the question mark. Okay, so the thing is the following. Let's say I output precise VO, let's say I output a value somewhere here, and then too much noise got added. So by the time the system saw it, we were here. Now there are no assurances being made at that point. And in fact, one way of thinking about it is at that point, the system is outside its operating regime. It's no longer digital. What happens at that point? All bets are off. There are systems which go into a crazy state called metastability. Excuse me. But basically, at that point, they start behaving like analog systems.
Okay, so the reason you add the like the little buffer is to prevent it from going in the yellow region.
Right. So this buffer and this buffer is to prevent going from the yellow region.
Okay.
Yellow region is the no man's land. You should not get there. If you go there, what happens is not defined.
All right, thanks.
No buffer to prevent it from going to the damage area.
It is usually taken, great question. It is usually taken care of when you design the chip. So you very solidly make one terminal to be ground and one terminal to be, it's kind of the equivalent to at your home. If you open an electrical panel or if you are installing a switch, you're supposed to ground it, right? So that's kind of the idea, because if you don't ground it, it can, the potential can go to something which above ground, and then even your neutral wire in the home wiring system may actually have a high voltage. Okay, so grounding, so solid, good ground is how you achieve it. Yeah. Any other question? Okay, great. So that yellow zone is a no man's land. All bets are off there. Okay, so now let's move to how do we encode information digitally. So let's say I'm designing a robot. It moves around the room. It has some observed things, and there are various things about the environment it needs to represent. So, for example, it may need to represent whether a door is open or closed. Well, that's easy to represent. There are two values. They obviously map. I can say open door is 0, closed door is 1, or vice versa. Okay, I can decide on a convention and kind of stick with that. So the easy case, therefore, is when the set of values I want to represent is the same as the set of values my hardware supports. So if my hardware is binary, if I need to represent two things, that's trivial to do. If my hardware represents 4 values, right, well, maybe 4 voltage levels, something like that, then I can easily represent up to 4 things, right? So that's the easy case. So in our door example, that's trivial. Okay, there's a convenient mapping. But how do I represent things where the set of things I want to represent are more than the set of things my hardware is capable of representing, right? So, for example, if I have a binary hardware which has 2 values, 0 and 1, and I want to represent this set of stones. So how many stones do I have? I have 8 stones, right? 1, 2, 3, 4, 5, 6, 7, yeah, 8. So I have 8 stones, or set of them. So how do I 8 different colors? So how can I represent it? So you use 3 bits, right? With 3 bits, a set of 3 bits can represent 8 different things. I can then map one of them to red, one of them to yellow, and so on and so forth. So, so I just begin to group bits like that. Okay, so I have 8 colors, and so one possible is that I can give them 3 bits. Can you think of some other way of representing? So sure, 3 can do work, and of course, with 3 bits, there are many ways of mapping to it, right? I mean, I can, for yellow, I have 8 choices. For red, I have 7 choices. So I have factorial 8 different ways I can do that mapping. But am I required to use 3 bits? Can I do it in 2 bits? Obviously not, because 2 bits can only represent 4. How about 10 bits? Or, right? I mean, can I use more bits than 3? I can, right? I mean, so I can, for example, I can have 8 bits, and so I can think of the color being represented by 8 bits. First bit would be 1 and the rest 0 if it is yellow. Second bit would be 1 and rest 0 if it is red, and so on and so forth, right? So there are many different ways I can encode. So when he said 3, it was, I need at least 3, but I can certainly have more, okay? And those would be different ways of encoding. This other example I gave, where I kind of said yellow is 1 0 0 0 0 0 0 0, red is 0 1 0 0 0 0 0 0, and so on and so forth. This is called one hot coding. So basically, we are saying 1 bit is 1 and the rest are 0. Okay, 1 bit is hot in terms of electrical. Okay, so how many colors can we represent with n bits to the power n? We already discussed that. How many bits do we need for m colors? Anyone? For 8, we needed 3. For m, how many would we need? Log base of m and ceiling of that. Yeah. Okay. Okay. So this is, of course, with binary. You can obviously do the same thing with other type of. There are computers where the basic unit is more than 2. Like, for example, apparently, I mean, I don't have first-hand knowledge of it. I've just read about it. In Russia, 3-valued computers were very common. Okay, so each position can have 3 values. Okay, so let's say you had a 3-valued computer. Okay, yeah, each wire can have 3 distinct values. Okay, let's call them whatever, ABC or -1, 0, 1 or so on, or 0, 1, 2 or something like that. How many tricks, let's call that TRIT, how many tricks would I need to represent 8 colors? Anyone? So, huh?
Like 8 bits.
You know what I mean? It's just more.
So we have 8 colors. We have 8 colors, and
So
I have a
3 bits, 3
computer.
bits, 3 bits.
We just want to.
Yeah, so we'll need 3 tricks, right? I'm just calling it trick. Okay. So, or you can say log to the base 3 and see. Okay. Okay. So, so I can kind of work that way. Now, in general, my value that I have may be some continuous value like sound pressure or light intensity or something like that, in which case the first thing I need to do is to decide how much do I want to quantize it. So if someone tells me, let's say I'm measuring car tire pressure. So the decision I'll say is, car tire pressure could be as low as 0, obviously. And what's a typical high-end one? Maybe trucks and all have it at like 100 PSI, pound per square inch. So, and then we can say, maybe I need to measure them to 0.1 PSI. So I have 100 PSI times 10 because I want a resolution of 0.1. So I need to be able to represent 1,000 different values. And then I'll say how many bits I need to represent 1,000 different values. Well, log 1,000 base 2, and that one is how many bits? Anyone? How many bits do I need to represent 1,000 different values? Yeah. So these things you'll have to develop. Should be quick. 8 is 256. That's 1 byte. Okay, and so 2 more bits takes us to 1024. So 1,000 would give us that. Okay, so let's say I have a thermostat where a temperature sensor gives it readings in range of 68 to 82, and I need to know it to a resolution of 2 degrees Fahrenheit. How would I represent it, right? So I need values 68. So 68, sorry. 68, 70, 72, 74, 76, 78, 80, and 82. So I have 8 possible values. And so I would then represent them using at least 3 bits. So I could do it this particular way. Now, how many different ways of assigning, encoding these temperature into 3 bits? There are many of them, right? There is, why did I make 68 to be 000? Why not make 68 to be 101? Well, this is where the task you are doing makes sense. So is important, because when I look at this, I should probably be able to say something about which temperature is larger or smaller relatively easily, right? I mean, there's some operations I want to do. So it kind of makes sense that I think of the bits as base 2 numbers and assign smaller one to 68 and the highest one to 82, and in sequence in the middle, because that will make it easier for us to imagine, given the temperature in terms of its 3-bit mapping, whether it's higher or lower than another temperature. I can easily get back to the actual numerical value. So not all encodings of 3 bits are going to be equally convenient. Okay, some are going to let us do our job easily, and the others are going to be harder. And something that we'll see again and again, at this level, don't think of 000, like when we are doing the mapping, it doesn't mean that 000 means 0. 000 is just a bit pattern 000. If it was my rocks of different colors, then there is no such notion that yellow comes before red or after orange or anything like that. They're just 8 different colors. But here we are dealing with temperature, and 68, 70, 72, 74 to 82, they're not just, there's an order among them. And it kind of makes sense that perhaps I should assign those 3-bit values such that some mathematical order is maintained. And therefore, if now we start saying, oh, let me think of those 3-bit values as base 2 numbers, and then I'm going to represent them in this particular order. So now let's say the system tells you that the bits that exist are ABC, right? So for example, let's say someone told you that the bits I'm seeing is ABC, where A is 0 or 1, B is 0 or 1, C is 0 or 1. What is the numerical value of the temperature if I tell you that the bits are ABC? There you go. So I'll let you ponder over it, but I should be able to come up with a formula where given A and B and C, each one of them is 0 or 1, I should be able to come up with the numerical value of the temperature. Anyone wants to take a quick stab at it?
68 plus 2 times.
2 times the binary representation. Yeah. Now you can see that this particular representation makes it easy. If I had some more random representation, so what he's saying is that I can go from this to the temperature by saying 68 plus 4A plus 2B plus C. That will give me the numerical value of the temperature there, right? I mean, so if ABC is 0, obviously I get 68. If ABC is 001, then I get sorry, I forgot, times 2. So then if ABC is 001, I will get 70, and you can test others, okay? So, but the reason I'm able to write down this succinct formula is because of the way we assign the mapping, right? If they were jumbled up, then maybe it will take a more elaborate expression to kind of do that mapping. So long story short here, really, I may have many equally efficient mapping in terms of how many bits they use, but they may not be equally efficient in terms of the task I want to do, okay? And just something to bear in mind. So multiple ways to represent information. This, I can have another one. This one is called literally thermometer coding. So 68 is all 0, 70 is 0001, 72 is 00011, and so on and so forth. 82 is all right ones, 7 of them. Why do you think it's called thermometer coding? Looking at it, can you think of why the name thermometer in coding? Yeah. Exactly. So actually, if you imagine kind of the old mercury thermometers or alcohol thermometers, right? Imagine them sideways, more temperature, the length grows for the mercury. So that's kind of what it's representing. Think of the one as the mercury. So 68 is the lowest temperature, mercury is at its lowest level, and then it starts increasing. So that's why it's called thermometer coding. Okay. I can also represent using 8 bits in this particular manner, okay? So there are variety of ways one can represent, and this is a one-hot representation, and some of them are make some things convenient, some of them things other convenient, right? So we'll look at some examples. So obviously 3 bits is very compact, and it makes it easier to compare things. With one-hot coding, it's easy to detect bit errors. In case of one-hot coding, if somehow some bits were to flip, and I were to see a signal which has more than 1 bit which is 1, or no bit is 1, then we immediately know that something is wrong. So detecting errors would be another part of the thing. Can I easily detect that my signal is corrupted? Whereas with 3 bits, the challenge is that if some bits flip, it's another valid value. So I have no way of detecting noise being there. In your computers, noise is a reasonably serious problem. So if you buy computers, sometimes they have these memories in them, which are called error correcting memories, which can tolerate some corruptions of memory bits that may happen, for example. So how you code affects compactness, affects ease of some operation, and affects how robust you are. In your software courses, hopefully you have seen how you design data structure. So if someone would ask you, how do you represent colors in C++? So, well, you'll probably define a struct or a class, and then you'll say, okay, how will I represent colors in there? Well, any one of these strategies could work, or some others also. You may even use enumerated types and so on and so forth. So there are a variety of ways we can represent information digitally in software, and the same thing holds true in hardware. So last bit, how do I pick the encoding scheme? Well, let's start something. How to encode a date, okay? The calendar date. So a very common approach is that how many days have passed since a given base date. So we can say base date is January 1st, 0000. Anything weird about it? Anyone? No, there was actually never a year called 0000. 1 BC and then came 1 AD. The book uses 0000, which is kind of weird because that date never existed in history. So, but you're right. It doesn't. Whatever base date we are picking, we can't go before that either. So now we can say, okay, maybe I'll pick a base date which is like, I don't know, Earth is 4.5 billion years old, so we can pick something which is that far back. Okay, so but these guys are. The textbook is supposedly picking the transition point between AC and BC and AD. So how many bits do we need to represent that? Your question? Huh? Yeah, okay. So 2020 times 365, and the book was from uses 2020, nowadays 2024, still would be the same thing. So 20 bits for the date. Okay. We can then say, okay, how about we actually want to know month and day and year? We can separate them out, right? I mean, so if I give you how many days since January 1, 0000, then can you get what month we are in from it? Yeah, right? You can count away the years, account for leap years, account for different days in the month. I can certainly do it, but that operation would be non-trivial, right? So if given that 20 bits, I want to, you give me the date, which is in terms of how many days since January 1, 000, and I were to ask you, by the way, what month is it? You will have to do that elaborate computation. And that's what I mean by some tasks are hard, depending upon how you represent things. So maybe I need to know month very quickly. So in which case I'll say, instead of representing how many days since January 1, let me represent things as 3 fields: month, day, and year. Now let's think about how many bits will I need now. So how many bits do I need to represent month? We have 12 months, so I need 4 bits. How many bits do I need to represent day within a month? The maximum is 31, so 5 bits, right? So 4 plus 5, 9. And then I have year, that's 2024, that we are still at 20 bits, okay? That's where your 11 was coming from. So 20 bits in either case, but as you can see, some things are easier in one, some things are easier in the other, okay? So clearly finding out what month is it, am I in the middle of the month, those kind of questions are easier with the second representation. Can you think of something which is easier in the first representation?
Getting the date of tomorrow.
Getting a date of tomorrow is very easy, absolutely, because in the worst case here, I may be spilling over to the next year. I may have to check leap years and all those kind of things, right? Yeah, exactly. Great. Sometimes I also want to know, is it a weekend, right? Again, I can do that computation, knowing what day it was on January 1st, 0000, and then work that out. But maybe I'm better off by actually explicitly also maintaining the day of the week. Now I will need 3 more bits for day of the week. And so now I have 23 bits, which is redundant. I need more bits than I strictly needed. So this kind of encoding is called redundant because the same information about the day of the week could be obtained from the other 3 fields, but it just makes computation easier. Okay, so just something to keep in mind that there is no one good magical representation. It's a design choice, and that design choice is dictated by what is a task you are doing. Do you see a problem when you have redundant bits? In general, philosophically, if I'm representing a piece of information where I have redundancy in the representation, does it make something harder?
Wouldn't it be better because like it makes it more like if there was an error, it would be easier.
Okay, great point. It actually can detect error. So there's a counterpart also. So in software, there is also a principle: don't repeat yourself. Okay, because it makes consistency harder. So someone may decide to update the date, but forgot to update the day within the week. Okay, so now you have conflicting representation. Okay, so which is kind of, I'm making the point from the other direction that you are. But basically, anytime the same information is represented 2 ways, you have to make sure it remains consistent throughout. Okay. Okay. So let's take another one. Playing cards. Okay. So I'm sure at least some of you must play cards. How do we encode playing cards? The playing card in a standard Western playing card deck. It has 52 cards. So I could number each card. I can decide some ordering. Usually spade is the highest and clubs are the lowest, and kind of there's a rank order within them. So I can say 52 cards, I need 6 bits. Okay, I could do that. I can do the suite, 4 suites, so 2 bits for that, and a number within that, 13 cards, so 4 bits for that. Again, I need 6 bits, but now it makes certain things easier. I can more easily tell whether it's a spade or not, for example. Okay. How about a 5-card hand? Maybe you're playing a game where you need to represent a 5-card hand. Well, in that particular case, I have some 2.5 million plus possibilities. I need 22 bits to represent a hand like that. Okay. So maybe I'm designing software or hardware for a card playing machine. You'll have to make these kind of decisions that you will have various quantities to represent, and you'll have to figure out how to represent them in hardware. Not very different than if you're writing a program in CS31, you'll have to figure out how to represent that information in data structures. So this is kind of like the data structure counterpart on the hardware side. So have we learned a best way to encode information into discrete value? What would you say? What's the moral from today's lecture? Did I teach you how to encode the one best way of encoding information? No, the message is there is no one best. Okay, you can certainly talk about how many minimum bits it will take. That's a valid question, but as to which way is the best depends on what you are seeking to do. So no best way depends on what you need to do. Goodness depends upon the operation that you are seeking to do. You can ask questions like which is more efficient, which is more tolerant of some errors being made, easier to specific. Some things will be easier. So let's go with this thing. This is our calendar example. So we have this 9-bit representation, which is 1 through 365 within a calendar, month, day of month, or month, day of month, day of week. So determining representation of tomorrow is super easy with 9 bits. I just add 1 to it. It's easy even with 4 plus 1, kind of because it's month and day, but it's a little bit harder, but still relatively easy. And this is also kind of a little bit harder, still relatively easy. Determine if 2 days are in the same month. Now that gets hard here with the 9-bit representation, right? I give you 2 dates and are they in the same month? Even if they are even 1 day apart, they may be in different months, right? So you'll have to kind of work through that. This one is easy, and this one is easy. Determine if one day comes before another. Well, with the 9-bit representation is easy. With this 4 plus 5 months is easy-ish. There is still, I'll have to do a little bit of a comparison of month and day separately. And this one is also easy-ish. Okay. So again, determine if day is a particular, if a day as encoded is a particular day of the week. That's hard if all I have is the index from the first day. It is hard here also because I still don't know day of the week, but here it is easy. So redundancy, those 3 extra bits made finding whether today is an off day or not kind of relatively easy. So representation is really going to be this balance between efficiency and the task you seek to do. And oftentimes in many systems, even the cost of an extra bit is too prohibitive because usually memory is one of the more expensive part of our systems. So you don't want to willy-nilly throw things around. This is not something you encounter in software courses because you are writing tiny programs on a big computer. But if you're working with tiny computers or designing a chip, then every 1 bit extra, and if you're storing 1,000,000 bits, then there's 1,000,000 bits extra, and that adds up. So oftentimes we do need to be clever about encoding. So to summarize, digital systems have discretized inputs, discretized outputs. Binary representation is the most standard way of doing things because it's easy to implement 2 states, and it's also very robust to do it. Okay. Choosing binary representation, which particular representation you pick for your task is a decision. One of the things that we most commonly try to represent in computers are numbers, integers, real numbers and all. And we'll talk about that later in the course a little bit. For now, anything which is a discrete set of values or even a continuous set of values like our temperature, we kind of roughly know what we want to do. Sometimes things that we are trying to represent are just unordered. Let's say I want to represent students in this class. There is no particular order among the students unless I impose one. I can go by the names. I can go by your student IDs that impose the order, and then UCLA for whatever reason picks our IDs to be what? Nine digits, right? We have 9-digit IDs in the campus. So hopefully UCLA, I guess, will eventually at some point have to roll over IDs. So all systems like these pick some stuff like that. There are in our computers, in our Unixy computers like Linux or Mac OS X and all, the days are the time is represented within the computer in terms of time elapsed since when Unix was invented back at AT&T Bell Labs in 1970. So they count as time elapsed since that time. And that is supposed to roll over in the year 2038 or something like that. So kind of the clock is ticking, and at that point in time, we'll kind of roll over back to 0 because we have only so many bits. So sometimes these representations are not future-proof enough. Actually, there was an interesting thing that I learned, read about recently. So all of your undergrads, perhaps some of you applied for federal Pell Grant or student aid or something like that. And this year there's a major fiasco going on where they rolled out a new financial aid system, the federal government, and anyone who was born in the year 2000 is unable to apply because the system barfs on that. Clearly, they made some screw up in the underlying representation of the information. So there is the whole college financial aid system is stalled because of that. So representations are important to get right. If you don't pick the right type of representation, you can make your system very inefficient, either in memory or computation cost, and all of those things kind of. Okay, so with that, I'm going to stop, and I'm going to see you guys again tomorrow, but on Zoom. And then we are going to start at how to operate on these values. Okay.
you.
Yeah, thanks, guys.